Welcome to Mark's Tech Talk. In this video, we're going to analyze a DC ladder network. So with a DC ladder network, we have a ladder type arrangement, and we're going to try to figure out the voltage on the right-hand resistor, in this case R4. In order to do that, we kind of work our way up the ladder, finding equivalent resistances along the way, and then we work our way back down the ladder in order to find voltages on the individual equivalent resistances until we get all the way back down to R4, which is what we're looking for. So we'll start out by looking at R3, 4, and 5, recognize that they are in series. So we're going to add those values to find the equivalent resistance. So 3, 4, and 5 are all 1K, so that would be an equivalent resistance of 3K. So I have redrawn that with the equivalent resistance. I've represented that with a little rectangle to remind me that it is an equivalent resistance, and that value is 3K. Now I'm going to combine that 3K equivalent with a 1K at R9, and remember, two parallel branches, we do product over sum in order to find the equivalent resistance. So if we do that, we get R3459, and that would be a value of decimal 75 kiloohms. Decimal 75 kiloohms. Now we're going to do the same process. We're going to combine that equivalent resistance with R2 and R6, and that would come out to 2.75 kiloohms. So there it is. Now we have the 2.75, and we put that in parallel with the 1K, and when we do that, we get a value of 0.73K. 0.73K. Now, if we have a simple series circuit, we can find the voltage across that 0.73K by using the voltage divider formula. It's just the source voltage multiplied by the multiplied by the resistance we're measuring across, divided by the total resistance. So that would be 20 volts as a source. We're measuring across the 0.73K, and dividing by the total resistance, which would be 2.73K. Do that arithmetic, you should get 5.35 volts. 5.35 volts. Now that 5.35 is across that equivalent, which is also the R8 in parallel with the 2.75 equivalent. So that same voltage across both of those. So we can kind of break that down again and say, okay, well, that equivalent is actually 2 1Ks and a 0.75 equivalent, and we have that 5.35 across it. So let's find the voltage across the equivalent. Again, we'll use voltage divider. 5.35 multiplied by the 0.75K and divide by 2.75K. That will give us the voltage across the equivalent resistance. And that arithmetic works out to 1.46 volts. So 1.46 voltage across the equivalent resistance. And that in turn is actually two resistors in parallel, another equivalent, and a 1K. So we can kind of work that way back down and say, okay, the 1.46 is actually across the three resistors on the end, R3, R4, and R5. We want the voltage across R4, so we do voltage divider one more time. This time it's 1.46 volts times the 1K, divide by 3K. Again, that's that last branch there with the 3 1Ks. So we get 0.49 volts as being the voltage across the 1K, and that is actually the voltage we're looking for, V4, voltage across the R4. Comes out to just under half a volt. So that's how we do a ladder network. Let's try it again. This time we'll use unequal values of the resistors. So let's choose easy values that are easy to remember. I chose values that corresponded with the resistor numbers just to make it easy to remember. So again, we're going to try to find the voltage across R4, which in this instance is a 4K resistor. So we're going to start out with that right-hand branch and find the equivalent resistance. We have a 3K in series with a 4K and a 5K. So that equivalent resistance turns out to be 12 kiloohms. Now the 12 kiloohms is in parallel with a 9 kiloohms, and we get 5.14 kiloohms. That in turn is in series with a 2K and a 6K. So the equivalent of those three works out to be 13.14 kiloohms. The 13.14 is in parallel with an 8K, and do that product over sum, and we get 4.97K. And now we have a series circuit. We can do voltage divider. This time our source is 100 volts. 100 times 4.97 divided by the total resistance. In this case, it's 12.97. And doing the arithmetic, we get 38.35 volts across that equivalent resistance. And just like before, we're going to break down that equivalent into our two resistors that we had in a step previous. That's a 13.14 and an 8K, and 38.35 is across both of those. And then that right-hand equivalent is actually three resistors in series, so 38.35 is across the combination of 2K, the 5.14, and the 6K. So we look for the voltage across the 5.14K, and that would be voltage divider. So 38.35 times 5.14 divided by the total, 13.14K, and you get 15 volts. Keep going with this process, and we have 15 volts across two branches there, the 9K and a 12K. And the 12K in turn is actually a combination of 3K, 4K, and 5K. So we have 15 volts across those three resistors. Voltage divider, so 15 times 4K divided by 12K gives us 5 volts. 5 volts across the R4. We'll call that V4. And that is our answer. So I went through that rather quickly. My suggestion is kind of rewind the video and pause it and do the calculations each time, find the equivalent resistances and do the voltage dividers, and make sure you are able to do each one. And again, just verify it by pausing it periodically, and hopefully you'll have the same answers I did. Now in practice, oftentimes these ladder networks look more like this, and as you can see, if you did the previous one, this one actually would be pretty easy. We actually have no resistors on the bottom, so it's a little bit easier to find the equivalent. So hopefully that will help you find the values you're looking for in a ladder network. That's this edition of Mark's Tech Talk, and stay tuned for more videos. Thanks for watching.